Good afternoon, everybody. Today I am going to discuss DC biasing of BJT. BJT means bipolar junction transistor. Basically, it is called transistor. In the last class, we have discussed about the current gain parameter alpha, beta, as well as gamma. So there is three possible combination, that is current, common base, common emitter, common collector. So common base and common emitter is usually used in the amplification purpose. Okay, and common collector normally used in impedance matching. Today I am going to discuss that is BJT DC biasing of BJT. Okay, what do you mean by biasing? That I have already told you. Biasing means application of external voltage to extract a response of the device. Response of the device, the behavior, output behavior, operating condition, operating limit. Operating limit means what is the maximum current achievable, maximum current, maximum voltage you have to give. That is all other parameter setting is understanding of DC. This parameter is very essential. Suppose another example I want to give you so that you can easily understand the mechanism, why it is necessary. DC biasing of BJT is why it is so necessary, and also setting of parameter. Suppose we want to apply transistor in specific purpose. Suppose we want to use transistor as an amplifier. So we have to know what is the operating voltage, what is the maximum achievable output using transistor, what is the frequency response in case of AC. So application design, that is analysis and design of transistor or any device using transistor required understanding of DC as well as AC. Proper setting of parameter affect the proper setting of parameter in DC analysis affect the AC analysis. Also parameter setting and vice versa. For example, simple example I want to give you. Suppose you want to perform a dance competition. Okay, what you will do? Basically, normally what you will do, you will do practice in your home. Okay, after once you ensure at which angle your performance will look good, everything once you know in your home practice, then you will go for the final practice. Similarly, in case of an electronic device, and in order to apply that device or design of that device or analysis of the device required understanding of this DC as well as proper setting of parameter. This is called DC biasing. So this is the aim. We want to establish the proper operating condition, that is of the device, that will help to analyze as well as design of any electronic device. Okay, that is why DC biasing is important. But why it is called DC biasing? Because at input we can apply DC as well as okay. Now I will start, then you can easily understand DC biasing, it will be better for you. So there is a two possible configuration I will discuss in this class. There is one is called fixed bias configuration, one is called emitter bias configuration, and first one is a fixed bias condition. So DC biasing, under DC biasing I will discuss fixed bias configuration. Fixed bias configuration. What is a fixed bias configuration? You can see this is a transistor. Transistor is represented like this, and you can easily identify. Arrow mark is this side. This is base terminal. This is collector terminal. This is resistance. Okay. This is capacitor. This is output. This is a grounded, and output is measured in between this. One terminal is here, and another terminal you have to put ground. Okay. This is the external input voltage, it is represented as RB, and this is connected at VCC. VCC power supply voltage, and this is AC. this is capacitor 1, this is capacitor 2, this is RC, this is a collector terminal, this is a base terminal, this is emitter terminal. Okay, since the arrow mark is down outside, so it will be not to point in, means it is outward. Emitter is outward, means this is NPN configuration. Okay, NPN register. So in case of PNP transistor, it will be, everything will look like only direction of current will change. Now it is emitter current is toward this direction, then collector current this direction, and base current this direction. Okay, clear? If it is PNP transistor, then emitter will be inward direction, then base current outward, and collector outward. And all calculation, everything will remain same. This is NPN transistor. This circuit is known as a fixed bias configuration. Now, because it is fixed bias DC configuration, once we going to understand or analyze this circuit in under DC condition, we have to replace this is a DC equivalent circuit. We have to remove the capacitor. Okay, well, I am drawing first. I will draw the diagram. Then I will tell you why I am writing this. This is a DC configuration. This is emitter. This is ground. This is base terminal. RB, and this is RC. This is VCC, plus VCC, and VCC. Okay, this is a DC configuration. This is IE will be. You don't confuse. You can join also, no problem. If you want, you can join also, no problem. Okay, in order to avoid confusion, I am writing this is DC configuration. Why? Because this is original circuit. This is a fixed bias circuit. And this is a DC equivalent circuit. Why this DC equivalent circuit? Because this is a capacitor. Capacitor block the DC. In order to analyze the circuit under DC condition, we have to remove the capacitor. Why? Because you have analyzed XC. XC is a resistance due to capacitance is equal to omega 1 by omega C. Okay, in case of DC analysis, the frequency of DC analysis frequency is 0. So 1 by 0 is infinity. So that means this capacitor totally block the DC. It will only allow to pass the AC. So that is why XC means resistance due to capacitance. So in case of DC analysis, we have to remove the capacitor. Is it clear? We have to analyze the circuit after removing the capacitor from the circuit. Okay, this is only in analysis. Okay, but in original circuit, capacitor will be there. We simplify the circuit under DC condition so that we can easily understand. That is why this is the equivalent DC circuit. Okay. This is clear. This is equivalent circuit. Now I will analyze the circuit. There is a two part. One part C. This transistor, although it is look like this transistor combination of like that. Three part. One is this is suppose emitter, this is base, and this is collector. Collector terminal is this one. This terminal is equivalent this one. Okay. Emitter is this one, and base is this one. This base connected the resistance. This is RB and VCC. Okay. This part is the input circuit. One side. Okay, now we are going to consider DC biasing. That's why I removed the capacitor from this side and capacitor from this side. Okay, now I am going to remove the circuit. Now I am removing the DC fixed bias circuit. Now, if we look at this circuit, then what you can understand, this is the input part. See, I can draw another diagram so that you can understand. This is a transistor, you can replace like that. Okay. This is emitter. Emitter means this one is emitter. This one is collector. This one is base. So this is a base terminal. This is collector. Okay. Collector is connected to resistance. This is RC. just remove the diagram. Okay. Emitter is this one. Emitter is grounded. This one. Okay. And this base connected to RB. So what I mean that I will analyze this circuit first. This is a input circuit. Input circuit cover emitter, base and RB. So this part is emitter. This part, that means we have to include one VCC, RB and one diode. Okay. So the analysis of fixed bias circuit combination of two parts, that is, I have already told you, in order to use transistor in active region and as well as amplifier, we have input circuit must be forward bias and output circuit is reverse bias. So forget about that. Now I have, what is the input circuit? Input circuit is this one. So input circuit, I can for you I can simplify that this one. Input circuit A, input circuit that is base emitter junction, that is base emitter loop. Okay, base emitter loop means this is base and emitter loop. This is input circuit. So input circuit I can draw like this. See, this is RB. This one, VCC is connected. This is VCC. This is connected to ground. VCC. This is plus. This is minus. Okay, and this is connected to transistor. There is a base terminal. This is emitter. You can join also, no problem, you can join also. This is input circuit. Then output I will discuss later. First I will discuss the input part. This is RB, this one, this is transistor, I will consider input part. This is emitter and this is RB. There will be IB current, kill, and there will be voltage, base emitter voltage VBE plus minus. Okay, this is the emitter and input circuit. Okay, I remove this part. First I remove this part. Now input circuit, if we apply the Kirchhoff law, what is the voltage? This is, you see, according to Kirchhoff voltage law, according to Kirchhoff voltage law, according, I will draw this circuit. This is smallest diagram I can draw, so that I don't want to remove. This is emitter down, this is base terminal, this is RB, VCC plus, this is power supply. Okay, this is RC, this is original circuit. Okay, now I want to draw the input circuit. Input circuit means base emitter loop. Okay, base emitter loop is, I again draw. This is RB, this is transistor. This part right hand side I am not drawing here because I am going to discuss the input circuit first. This is emitter, this is plus, this is minus, this is a ground. Okay, you can ground here also, no problem. And this is base and emitter. This is emitter, this is base, and VBE, base emitter voltage will be there at the junction. I have already discussed. This is emitter current, this is IB. Clear? Okay. Now same diagram. This diagram I am writing for better focus. Okay. This is VCC. Now from Kirchhoff law, from Kirchhoff's voltage law, what we can draw, there is VCC, this is minus. Okay, focus it, minus plus, we are going from minus, so minus VCC, okay, plus IB, RB, okay, plus VBE equal to 0 according to, or you can say, if I say VCC equal to IB, RB plus VBE, is it okay? That means total voltage, total input voltage, that is power supply voltage, is distributed in in RB as well as VB. Suppose I have 500 rupees, so 500 I will distribute it between two students. One get 200 rupees, another get 300 rupees. Okay, that means 500 equal to 200 plus 300. This is suppose 500, 200 plus 300. That means total output voltage is equal to total input voltage, that is power supply voltage VCC, is equal to voltage appear equals resistance RB plus voltage VBE. Voltage equals base emitter junction. Okay, this equation. This equation, from this equation, what is the aim of this equation? Aim of this equation, we are going to calculate the current, input current, possible input current of the input circuit loop. The IB equal to VCC minus VBE divided by RB. Okay, do not confuse. RB is the external input resistance. It is not input resistance of the circuit. Do not confuse. This is the external input resistance. Okay, but it is not internal resistance, input internal resistance of the circuit. It is we are giving external. Okay, this is the calculation. This is in input circuit. Okay. This is we are going to calculate A. A means from this circuit I am getting IV value, base current value I am getting VCC minus VBE RB, equation number 1. Okay, from input circuit loop. Now I am going to output circuit means which one? Output circuit means which one? This part we are going to discuss. Which part is common? Output circuit is which one? Output circuit, this part. This part we are going to discuss. Output circuit. Input circuit we have to discuss this part, and output circuit I will draw the output circuit. This is output circuit, emitter collector region, collector loop. Okay, output circuit I will draw this part. I will draw here, so it will, you can easily see. This is emitter, this is base. Emitter is ground. This is RC. Okay, we are going to discuss the output circuit. This is VCC plus minus, and this is ground. This is emitter, and now it is VBE. Now VC is CE is the output current voltage. Okay, this is the output circuit. This is the output circuit. Then collector current along this direction. Now we have to measure the, according to Kirchhoff voltage law, according to Kirchhoff voltage law, what is the equation? Look at this equation. Minus VE, first minus VCC, clear? Plus IC RC, okay? Plus VC equal to 0, or you can simply say that VCC is the total input voltage equal to the sum of product of current and resistance plus voltage according to voltage. So IC RC plus VC. Okay, or you can simplify VCE, collector emitter voltage, VCC minus ICRC. Okay, this is equation we are going to discuss. From this equation we are getting, I think it is visible, VCE equal to VCC minus ICRC. Okay, this is equation number 2. Okay. So basically we are getting two equations. From input circuit we are getting this equation VCE, from output circuit VCC minus IC RC. This equation A1. This is a fixed bias condition, and this is the way how to calculate the input current, that is IB, under consideration of input resistance, base emitter resistance RB, and output. This RC is a load resistance. Okay. So load resistance RC, or it is using input circuit we are getting this equation, and output circuit we are getting this equation. Now this is in fixed bias concept. Now I am going to analyze the load line analysis. This is fixed bias circuit, and calculation how to calculate the base current and base emitter voltage. This is the equation. Now load line. What is the load line analysis? Load line analysis. Operating point of the device. Operating point of the device. How to calculate the load line analysis and operating of a transistor is aimed establishing the proper operating parameter of the device. Okay. Now using this equation we have analyzed output carry from the output characteristic. We know the transistor operating characteristic curve. Okay. The transistor, this is VC, it has three regions of operation. One is cutoff region, one is active region, one is saturation region. This is suppose characteristic curve for a particular base voltage, IB, base current, sorry. And this is another characteristic curve. Okay. For a given, this is IC. IC means output current, and this is a input VC. So okay, load line analysis establish the curve from where we can estimate the operating condition of the device. You see this equation. This equation is similar to y equal to mx plus c. Here is mx, but it is positive. This is positive curve. If we plot this equation, you are getting this, but it is a negative curve. It will give like this. Now, from this equation, from A to equation, if we see when VC is 0, when IC is 0, this equation, A to equation, when IC is 0, so VCE equal to VCC. So this point is represented as VCC x-axis, y-axis, VCC is suffix, VCC 0. This point will be somewhere, look at this. This point is VCC, maximum voltage. Okay, when IC is output collector current is 0. This is analytical analysis. We assume that collector current is 0. Then using this equation, we are getting this point. Okay. Next, when VC is 0, see, when VC is 0, then IC maximum collector current equal to VCC divided by RC. Okay, then this point will be, this is a current getting this point somewhere between this one VCC divided by RC. Okay. Now we are drawing a point line. This is, suppose I am considering this IBQ. See, this curve is for a particular value of base current. Suppose this is 0, base current is 0 here. This is base current is 10 microampere, 20 microampere, so something goes like that. This is a characteristic curve. This region of transistor active region. This negative very close to the curve. This is suppose another curve. This region is called cutoff region, and this region is called saturation region. And for normally amplification of transistor, for amplification purpose, we often use transistor in active region. Okay, Now this point is a Q point. Q point means quiescent. Quiescent means silent point, inactive point. So in order to use transistor, this is a maximum achievable current, that is VCC divided by RC. And RC is the load resistance. If we increase the RC value, the load curve will decreases toward the downside. Now, what is the significance of the curve? Significance of the curve is that beyond this operating region, or this beyond the load line, so we normally never use in amplification purpose. So be within the curve, within this load line, we use for amplification. But here this point, suppose if I consider this point is VC equal to 0, this is on the device will be totally off. We will suppose we want to use the device in this region. Then in this region, the device will active. That means forward bias. If base emitter junction is forward bias, and base collector emitter junction will be reverse bias. But here in this region is I am drawing here. This region is saturation region. In this saturation region, the both input circuit as well as output circuit will be reverse bias. Forward bias in this region, and cutoff region both are reverse, and active region input circuit is forward and output circuit is reverse. This is the significance of load line analysis. Okay. So what I am drawing again so that you can easily understand. Simple curve so that you can understand. Suppose this is a characteristic of a transistor. So according to this equation, VC will be here, and IC is the output current. I have already told in the last class. So I draw a curve, single curve. This is a characteristic curve of a transistor, output characteristic curve of a transistor. This region, in this region, this is called active region. We often use transistor in active region. In active region, this circuit, base emitter circuit, is the forward bias, and another output circuit it will be reverse bias. But in this region is saturation region. This region, the both input circuit and output circuit will be forward bias. And cutoff region, this is a cutoff region is very close to the horizontal line. In this cutoff region, the both circuit will be reverse bias. And for amplification purpose, we want to apply transistor in active region. So forget about that. Now I am removing this part again. Now what is a load line? Load line analysis. DC load line analysis establish the proper operating condition of the device. This is suppose output characteristic. According to this equation, this axis is VCE. It is voltage. Okay. This is normally milliampere. Okay. If we consider VC is equal to IC 0, at this point what we will do? VC is 0, this equation, at suppose A point, VCE equal to 0, then what will get? VCC equal to IC RC. So IC equal to, from this equation, VCC divided by RC. So that this point is represented as 0 VCC divided by RC. Okay, that means here one point, VCC divided by RC. Similarly, when at this point, suppose this point means at this point, or you can consider any point. Now when IC is 0 means on the axis of the VCE. IC is 0 using this equation. So VCE equal to VCC. Okay, that means this point will be here, VCC. So this line is the point connecting maximum achievable current in the output axis, and the voltage is called load line, and this point is known as a Q point, and this curve is called load line. Clear? Any point this is below this curve is the device used in any point. Any point means, suppose if you want to apply, this is suppose you draw a characteristic curve and analyze the device. You take a point. Take a point means, what is the point? What is the value of this point? Suppose x, y. X, y means VCC, you will get a particular value of voltage, particular value of current. So at that point, if you use the transistor, it will active, it will operate properly. And outside this load line, you cannot use the device. You can use the device, but device will not properly function. Now, what is the properly function? What you can understand properly function? Suppose this is I am drawing again fixed by cycle. This is RB, this is RC, this is VCC, this is connected to base terminal, this is emitter is grounded, and this is capacitor, this is input circuit, and this is capacitor, this is output circuit. Okay, now I will go in the circuit. Suppose I want to use this circuit. Suppose I want to use this circuit for amplification of signal. So I have to know what are the maximum voltage, what is the maximum current, and what is the operating voltage that we have to set, through which we can easily amplify the signal. Now I have analyzed the output characteristic. This is VCC and this is VCE axis. This is IC axis and this is a load line. This is a Q point. Okay, this is VCC by RC. So I take this point, and this is the parameter setting. This is the proper value of current and voltage. And once we know this proper setting from the load line analysis, then we use that setting in this circuit. And after that, we will apply the input signal. We will get the amplifier output here without distortion. Without distortion means without losing the generality of the signals, without losing any information. Okay, that is why load line analysis is essential. Okay, next we are going to analyze the emitter bias circuit. So, what is the problem in fixed bias circuit? Although fixed bias circuit look like very simple, okay, and what is the emitter bias? There is a two configuration. One is a fixed bias configuration, another is a emitter bias configuration. Okay, emitter bias configuration is nothing, just generalized version of fixed bias configuration. Only they introduce a external resistance in the input circuit to stabilize the circuits, to enhance the stability of fixed bias circuit. Okay, so emitter bias circuit, two emitter bias. Two emitter bias circuit. Emitter bias circuit. Circuit is circuit. Okay. Emitter bias circuit, you focus on emitter bias circuit. This is suppose transistor. It may be NPN, it may be PNP, whatever it is. Suppose this is a base terminal. This is a collector, this is a base terminal, this is emitter. Now this is this is RD, this is RC, this is plus VCC. Okay, this is the output, capacitor output, this is C2. Now similar to fixed bias circuit, but there is another resistance, RE. Emitter resistance is introduced. This is input, S input, C1. This is emitter, this is collector, this is base, this is base. This is the emitter bias circuit. Why it is called emitter bias? It is similar to the fixed bias circuit. only only external resistance R is introduced in the circuit in order to enhance the stability of previous circuit. Okay, and similar to the previous circuit, we can analyze the emitter by circuit. Okay, now if we see the DC equivalent circuit is very easy. Just remove this part, remove this part, and just remove this part. This is the DC equivalent circuit of the device. Just removing the AC component. AC component means because capacitor block the DC, because we are going to DC analysis. So remove the capacitor, it look like the DC equivalent circuit of the device. Okay. Now similar to previous circuit, we can analyze the input circuit. So input circuit A, we are going to input circuit. Input circuit means what is a base emitter, emitter loop. So previously we have base emitter loop means you can draw like this. Collector part we are not going to discuss. This is emitter, this is emitter resistance, and this is RB is connected to VC. You can ground it, no problem. This is IB current. Okay, this is VBE emitter voltage. This is RE and IE current. This is the input circuit. Base emitter loop, we are considering base emitter loop. Then you can easily understand what is the value of current. Then it is start according to Kirchhoff law. According to Kirchhoff voltage law. So VCC is it visible minus VCC plus IB RB plus VBE plus IE RB equal to 0. Is it okay? Okay, so you can see, you can write also VCC equal to IB RB VBE plus IE RB. Is it okay? Clear? Now I remove this circuit. Okay, you can I have already drawn. I remove this equation and this part also. So VCC, I have already VCC equal to IB RB equal to VBE plus IE means what is the emitter current? You can see IE equal to IC plus IB, right? This lesson you have already know. So IC means what? Beta IC by IB, right? So IC means beta IB plus IB, so beta plus 1 IB. Clear? So I will replace beta plus 1 IB RB. So what you will get? IB equal to VCC minus VBE RB plus beta plus 1 RE. I remove this part. Finally, what I am getting here, you see, this is the equation number 1. What I am getting here, what introduction here, with introduction of external input resistance to the emitter terminal, that is RE, this terminal, this part is introduced with the input resistance and enabled with this part. Have you understand? That means this resistance RE resistance is reflected back to the input circuit. See, input circuit resistance, this is the input circuit. Input circuit resistance is RB. Now it is input circuit part because why it is reflected to input circuit? Because IB is the input current, IB current. So IB in calculating the IB base current, so this RE resistance play important role in the input circuit. Okay, this input circuit. So as a result, so in previous calculation what I am getting in fixed bias configuration, what I am getting, you see in fixed bias configuration previous circuit, what I am getting, IB equal to VCC minus VBE RB. This is the previous calculation. Here we are getting external part, this part. So because of addition of external resistance RE, which appear in the input circuit, is it okay? You probably understood. Appear in the input circuit means it is added with input resistance RB. That is why I am telling it appears the input circuit. Because of this addition, the IB base current is reduces. Why base current and input resistance? This input resistance IE beta plus 1 RE. This part is added to the input circuit. Because I have told you, for amplifier, for good amplifier, input resistance should be high. So high input resistance means more stable. So this external input resistance, due to introduction of external resistance in this emitter bias circuit, this appear with input circuit and it is sum with the input resistance RB. Because of this, IB current is reduces, and once IB current is reduces, see, beta equal to IC by IB. Is it okay? If we can reduce the beta IB current, base current, then what we can get? The beta gain parameter of the circuit we can increase. Okay, that is number one. Number two, if we increase the input resistance of the circuit, then we can stability of the circuit we can increase. Clear? So input resistance, external input resistance of the circuit is added, reflected with the input circuit, and that is why it is emitter bias configuration is more stable than fixed bias configuration. Both are used in amplification purpose. Okay, and similarly in the output circuit, if we see the output circuit, this is the input circuit we are going to calculate, and already calculate output circuit. If we see the output circuit, see, output circuit will be like that. Output circuit, you see, I am drawing here. Output circuit, I am drawing very small diagram. This is input. This is emitter. This is emitter. Okay, ground. Output circuit. This is collector. Resistance RC is there. Then VC, positive, negative, VCC. Okay, this is connected to this one. This is output side. Now VCE. Okay, VCE developed in this equation. This is RE. Okay, clear. This is the output side. Output side. So, according to Kirchhoff law, according to Kirchhoff voltage law, so VCC, if we see this way, or you can see move this way also, no problem. VCC equal to, what is the value? IC/RC, right? Total input voltage, that is this voltage, equal to the sum of voltage of across throughout the circuit. So first one is IC/RC, next one is VCE, next one is IE/RE. Is it okay? Okay. Now in this circuit, so I assume that because IE approximately equal to IC, so if I simplify this equation under approximation, VCE equal to IC/RE. So VCE equal to IC is a common, IC RE plus IC. This equation. You can simplify VCE equal to VCC minus IC RE RC. This equation. Okay. Now additional term, this one is increases. This one increases means the VC voltage is reduced. So what is the difference between now? If you see the voltage, if you see the load line analysis, suppose VCCE again in common emitter bias configuration, that is this is IC, this is a load line, this is a characteristic curve, this is the operating Q point. So this will be from this equation. If you plot VCC divided by RC plus RE. Okay, and this is VCE and this is clear. So finally a summary of the calculation I am writing here. Summary of the calculation in fixed bias, that is fixed bias circuit, fixed bias circuit, emitter bias circuit. What you see the comparison? Fixed bias circuit IB base current equal to VCC minus VB RB. Is it okay? In fixed bias. Here IB equal to VCC minus VB RB plus beta plus 1 RB. Is it okay? Here VC equal to VCC minus ICRC. This is second equation from the output circuit. Here VC equal to VCC minus IC RC plus RE. Is it okay? Here load line analysis. This is VCE and this is IC. This is a characteristic curve for a particular value of base current. Remember, I can draw a different number of diagram for different value of base current. This current is suppose this is a VCC, this is VCC, this point, okay, this point, VCC divided by RC. Here if I draw a characteristic curve like that, this is suppose IC, this is VCC divided by RC plus RE, and suppose this is a diagram, this is VCE, this is VCC, okay, this is a Q point, okay, this is the difference. So application of external input resistance to the emitter terminal result lowering down the collector current, okay, and also lowering down the input current. So what do we mean by that? Introduction of external resistance to the emitter terminal will control the output current as well as base current. And what actually we need? See, suppose particular value of beta. Beta means for a given transistor, beta is constant. Beta is suppose 50. Okay, if we increase the beta 100, in fixed bias condition, the parameter of abruptly increase. Okay, in order to calculate the parameter at a constant level, or in order to control the output parameter means suppose specifically for current output current IC, or in order to decrease the base current. So we have to introduce a external resistance like RE. As a result of circuit stability will increase. So you can, I will give you another example in the group. I will send you a question, numerical analysis, so that you can easily understand how introduction of external resistance in emitter bias configuration stabilize the fixed bias configuration. Now fixed bias configuration is a standardized version of emitter bias configuration is the standardized version of fixed bias configuration, and both configuration we use for amplification purpose. Our aim is to we have to amplify the signal in proper region with proper setting of parameter, so that the genuinity and proper information of amplified signal should be matched with the original signal. Okay, without loss of information. We have to amplify the signal. Therefore, proper setting of parameter is essential, and proper setting of parameter is obtained from the DC load line analysis. That is why this analysis is done. Okay, and beyond this calculation and this look very, I think it is look complicated for you, but once I started the hybrid parameter model, this analysis will be very easy. Okay, and after that I will discuss some numerical problem for which you can easily understand the stability analysis, why it is so essential. Okay, after this portion I will remove the I will move to the hybrid parameter model. Then you can and in using hybrid parameter model, H parameter model, RE model, then I will analyze the circuit. I will give the numerical. Right now I am not focusing on the numerical. I want to introduce some basic concept related to transistor and various combination of transistor, so that you can understand basic point. Okay, after that we will move for analysis. Thank you.